Okay, this is video 3 in the series on test 2 review, and we've been looking at the transfer function h of s is equal to 2s over 5s plus 1. We found the pole zero plot for that transfer function. We also found the final value and initial values for an input x of t that was equal to u of t, a unit step. And now I wanted to consider a different input, x of t equal to a ramp. Okay, ramp slope 1. All right, but before we do that, just one more comment on this final value here. If you're asked for what is the steady state response of the system, okay, then in this case what we really have is the input goes up like this and the output starts from 2/5 and it goes down to 0. Okay, starts at 2/5 and eventually goes to 0. So the steady state value is actually, or steady state response is actually 0. Now imagine a different situation where you put in a step like this, and actually what you had as a response was something that maybe did this, okay, in time. All right, so that kind of system, if you ask what is the steady state response, the steady state response of that system doesn't have a particular, doesn't ever reach a final value. It just keeps on growing. In fact, it looks like it has some kind of a slope times time and then some offset. All right, some offset. It'll be a negative offset, but that's what, you know, this ultimately this steady state line would look like. So that would be a steady state response in such a system. It wouldn't be just a constant. And in such a system, by the way, you can't actually determine the final value because the final value is infinite. So maybe we'll look at that system shortly. Okay, so let's put that to the side. I'm going to go ahead and just work another example here where we will look for the steady state response and the final value for the same transfer function, but now we're going to excite the system with a ramp. Okay, so we can write that if we take the Laplace transform of our input, we'd find that x of s is going to be now 1 over s squared, right? And we have the same transfer function. Okay, so when we multiply that, we're going to find, we'll say 1 over s squared. Okay, so that's the Laplace transform there. We'll get the s that cancels, and we'll get 2 over s times 5s plus 1. We can partial fraction expand that to an a over s plus a b over 5s plus 1. Using the cover-up method, we cover up the s and apply 0 to the 5s plus 1. That gives us 2/5. That gives us 2, I'm sorry, for a. And we cover up the 5s plus 1 here and plug in minus 1/5 here, and that gives us minus 10 for b. Okay, and we should probably reformat this as 2 over s minus, I'm going to divide by 5, so it'll be 2 over s plus 1/5. Okay, and here we can take the inverse Laplace of y of s, and that will be 2 minus 2e to the minus 5, t over 5, and the whole thing times our unit step. Okay, so this starts at 0. I'm sorry, starts at, yes, 0, and it ends up at 2. Okay, and this is for an input that is going up. So this is r of t, or that's our input x of t. right? And this here is our y of t. Okay, if you think about it, it makes good sense that this is what's going on. If I were to take the transfer function h of s equal to 2s over 5s plus 1, and let's write the ordinary differential equation. So we can write this as 5s plus 1 times y of s is equal to 2s times x of s, right? So this is 5 times y dot plus y is equal to 2x dot. So if we plug in a ramp here, this is r of t equal to t, what we're really solving is 5y dot plus y is equal to 2. All right, and I think you would agree that this should have a response that looks like a 1 minus exponential decay.